Yeah. So we will talk about the visual language models. So if you go, okay, so how do I, first minimize? So how do I get my picture? Okay, minimize first, then okay, good. Thank you. So we want to start, how the computer vision has evolved. So in the old days, the traditional model was we are given an input image, and we have some model, and we will get an output. Like we can give an image, we can classify what that class object image belongs to. Then in that thing, around 2012, this deep learning revolution started, and we have all these deep learning neural network, the CNN and so on, LXNet, ResNet, VIT, and all those things, right? So, so that is traditional model. Then we started with the textual prompted models. So we have input image. In addition to that, we have a textual prompt. So we are communicating with the model, with the language, with the text, and we'll get output. So in these examples are clip, as we have discussed, Flamingo, Pali, GPT-4, and we will go through in detail. So now these models are also called foundation models, right? So there's a bridge and there are these foundation. This picture from NVIDIA. So, I mean, there isn't a precise definition of foundation model. That, pretty loaded word. People have different meanings. But in general, the foundation models are trained on the massive amount of data, and they can be adapted to different downstream tasks. And so here's an example of that. So we have data, like we have text, we have images, we have speech, and we have structured data, 3D signals, and all kinds of things. So we'll use this to train a foundation model. Then we can adapt that model to different tasks. Suppose question answering, sentiment analysis, information extraction, image captioning, object recognition, and all those things. So that's kind of general idea. So now foundation models in computer vision, we have this textual prompted models. Then we have visually prompted models, and we have others. So in the textual prompted models, so we talk about clip. Clip is a contrastive model. So you have a text and image pair. We want to look at which are positive pairs, make them closer in representation space, which is negative, we're going to make them far apart. So contrastive. And we'll talk about other models also. So here, generative model where which is different, that we want to predict the next word, which will be output will be Flamingo and so on. We'll talk about that. Now CoCa is a model which is kind of combining the contrastive and generative, and that's actually next thing I'm going to talk about. And GPT-4 is a conversational model. So GPT-4 or JetGPT, you can say, is built on GPT, which is just predict the next word, but then you add this instruction tuning, then it becomes conversational model. You can ask question, answer you, and so on. Okay? So then we have visually prompted models where you give them input image, and suppose same segment everything is a very popular model, and different other versions, and you can adapt those. Same can be adapted to tracking, pointing, and so on. And then there are some generalist model which will do lots of things. We will talk about Painter. Then others are, which are heterogeneous model and also embodied model. Now these are the models like PALM-E, which will be used for robots. So you have an image, a video, you have text, but output will be control for robot, how to move, pick up object, and so on. So it's a pretty big area. And now different architecture styles is that we have image encoder, text encoder, it's called dual encoder, and clip is an example of that. So combining these two encoder, we will have loss function, contrasted loss, we learn the representation. So main idea is given an image or given a text, what is the base representation which computers can use? And that's the main idea. And these representation, old days we used to call features. What are the features? Because the image is just numbers, audio is just numbers. But what are the semantic features, some important information which we want to extract, and that's also called embedding, representation, and so on. So then there's another version, which is like a fusion, that we take the image encoder, text encoder, we fuse that, and then we have a decoder, and we get output. And CoCa is one of the examples, FLAVA is another example. We talk about both. So, so now next one is that we have both the encoder and decoder. So in this case, we have image encoder, text input, image input and text input, go to the text encoder, and we get decoder, and then we do the loss function on that. So in this case, Pali is one example. We'll go through that. So the last one is that we have the image encoder and text input. We have a language model, large language model, LLM. And we'll basically adopt LLM to be able to take input as an image and the text, and we can do visual language model. So Flamingo is one example of that. Or Blip2 is another one. Okay, so I'm going to talk about CoCa, which is CoCa is basically contrastive and captioning. That's what CoCa. It has both of these. Captioning is the generative. So Pali, Flamingo, FLAVA, Painter, Blip2, image bind, language bind, Lava, video ChatGPT, and so on. So let's look at first. So these are the papers. And these are very recent papers. So that's one thing you notice in the class. Typically, when you take a class, you learn some material which was maybe published 15 years ago, 20 years ago in the class. But here we are discussing papers published, a few months ago or 1 year ago, 2 years ago. But the field is changing so fast. There's a lot of things happening. So that's why we have to keep up. So this is called contrastive captioning or image text foundation. Okay, so foundation model, you will keep seeing this. And so this is from Google. Lots of fundamental papers are from Google, as I have been saying. There have been a lot of, there are lots of smart people and lots of good work. So contrastive captions are image text foundation models. So the way it works, that we have image, we have text, we encode the image, we encode the text, and this is called unimodal text encoder decoder. Then we will combine this is called multimodal text decoder. So here we will put a text and also the image, so that's called multimodal. So now up to here will be simple clip. So contrasted loss, image and the text. But then we will combine with the text here, decoder, and caption will come. Okay, so here we will say if the pair are same, we will have the contrasted loss, make them so that positive pairs come closer, negative pair fall apart. That's one loss. And the other loss will be the given image, what are the captions, should predict the caption, which is generative model, and we're combining these two. So, so the way this works, that we take an image, we encode, and all these are tokens. As we talk about VIT, 16 by 16 page is a token. And then we have words, and we encode these words also, get tokens, and then we will do contrasted loss between the CLS token, the last token, the special token, which capture the whole information, image, and all information in the sentence, contrastive, simple, as we discussed. Now these tokens go to this multimodal text decoder, and that's where we are combining now image information and text information. So here we will have a cross attention. So in the standard transformer, typically we use the self attention. We have same model, we make 3 copies. But here we will do the cross attention, and will come out the caption. So again, here as you see, the beginning of sentence, 2 dogs running in a field, and we want to predict the next word. So after the beginning of sentence, we want to predict 2. Then after 2, we want to predict dogs and so on. Okay. So if you look at losses, the first loss is contrasted loss, which is we have talked about this many times. So this is image to text. Okay. So X is the image and Y is the text, and this is the text to image. Both way, the matrix I showed you for clip, we are given image, we want to find the cosine similarity between all of the text, and then for given a text, you want to find cosine similarity with all the images. So that is and this is basically the dot product is the cosine similarity. Okay, so then the captioning is very simple, that this is the predict the next word. So given the words up to t-1, given an image, so Y is the text and X is the image, what is the probability of the next, the Y tth token? Okay, so we'll take these 2 losses, have some of these constant, we'll combine them, and we'll train the system like that. So now once it's trained, as we discussed, now we can use it for different things. So suppose we can just plug it out, image encoder, use it for like classification. So same thing when we're training the clip, we have clip and image encoder, clip text encoder, we train them, we can use just the clip image encoder for classification, or we can use both and so on. So this is one example, visual recognition. Second thing we can do, the zero-shot text retrieval. So we will have given an image, we want to retrieve what are the possible caption for that text. Or given a text, we want to retrieve all the possible images. So we can do, because they are in the same space, they are aligned, right? So then other will be that we can use for given image and text, we want to come up with the image captioning, say what this image describe that. So they use this JFT 3 billion data set, and which was larger than 300 million JFT, which was used in VIT, and they had about 30,000 label and web scale alt text data. So if you web page, we have these mostly text, but you have images also. So these people are going to use lots of those because there are millions and millions of websites, right? You can go and just scrape those. And they also can use the video. So as you know, video is sequence of frames. So in a way, you can encode each frame like an image and then combine them, simple max pooling, combining them like all the frames just average or some other ways. And then we'll representation for the whole video clip, and we can apply that. So they show these results, and you will see many of these papers will have this kind of, they call a radar plot, okay? So the idea is that we want to show that CoCa, this is the performance of that which is shown in this color, okay? Then they are comparing with Florence. We'll talk about the Florence also, which is green one. This is the SimVM, VLM, and this one. And then we have SOTA, the other some specialized model, this one.
It's not in that. That SOTA color is not there.
I think it's under here or something, right? So what is this one? This one is this, right? These are the, this is something similar. When you put on the top, of color changes, right? So you know how you combine the, how do you get the green or your simple binary colors you combine, you get, yeah, go ahead, which one?
Like red and orange makes, red and yellow makes orange, yes.
See? Okay. So they are comparing this with lots of these data sets. So here is the image to text retrieval, MS CoCa, zero shot. So zero shot, as you know, that we don't use any training data set from this MS CoCa. We just apply. We use some other data set, JFT. We want to try that. So this is the image to text retrieval. Given an image, want to retrieve the text. Yes? Then this is the zero shot text image retrieval. Okay, given a text, we want to retrieve the image. Then this is the another data set called Flickr. And again, image to text. And this is text image. Okay? And then this one is a VQA, visual question answer. We'll have an image, question, answer. This is another one we talk about these two. And then we have here zero-shot ImageNet, simple. Then we have video, actions, Connectic 800, 600, and this is 400. Then the the ImageNet, I think they probably fine-tune on that, no caps and all those things. So, so you have to show that your curve is bigger, right? Much better, otherwise paper will not be accepted. We just got reviews today for CVPR. They are horrible. And we got, decisions about iClear. Also, they came on the same day, right? In the morning, later. So that's the fact of life. There are so many data sets you have to compare and, try your better. It's in one way it's exciting, other way it's very brutal. So people spend so much time working on the paper, submitted, and then rebuttal and wait, and you say, well, it got rejected. Okay, so this is a new thing. They talk about visual entailment data set. So idea is that given an image, and you have, these are possible hypotheses. Two women are holding packages. The sisters are hugging goodbye while holding to go packages after just eating lunch. The men are fighting outside. So you want to classify this, whether it's entailment as a neutral or the contradiction. So as you see that this is like a contradiction, right? There's no men and so on. So this probably is happening, and this is neutral. You can say it's true, but not. Something like that. So there's, task. They evaluated on this one. There's another one. Here, what you do, we are given two images, and then each caption is paired with two images, and the task is to predict if the caption is true or false. So in this case, left image contains twice the number of dogs in the right image, and at least two dogs in the total are standing. So it's, kind of more complicated question. You want to see if this visual language model is able to answer. So this is, I think, correct, but here is incorrect because one image shows exactly two brown acorns and a back caps on green foliage. So I think there's only one, right? There's not two. So something like that. So they came up with, so again, this is kind of like a benchmark, or how do you test your model? You come up with more creative ways to come up with a different kind of question answer, different kind of data set, more complicated and so on. So all this is fine. Okay, so next one we are talking about Pali. So this is a multilingual language image model, and the pathways to language and image model, and that performs image only, language only, and image plus language tasks. And the thing is that it will understand different languages, okay? So, which is good. Not only English, but other languages too. So, system is very simple. So you have the image, VIT, and you have the text, and then you have transformer encoder. You combine them, decoder, and the output comes text. So it is a 4 billion parameter, a VIT extreme or something, and 13 billion parameter text model. So in these visual language model, you have the text and the image encoder, and then you have the language model, right? So the LLM, large language model, all these, GPT and Gemini and all those things, or the large language model are very huge, 7 billion, 71 billion, and so on. So, so here they are using T5. T5 is a good language model, after BERT is a T5. And then they use this WebLib 10 billion data set. So image and text in over 100 languages. 10 billion images and tens of billions of image text pairs. And these use different training mixtures, different data set, OCR, WebLib, cross-lingual, and so on. So the results are that they can do image captioning, they can do multilingual captioning, they can do visual question answering, they can do cross-lingual and multilingual VQA, they can do zero-shot image classification. So that's why it's called foundation model. It can do a lot of things. So suppose given an image like this, generate the alt text in English. So this is the output, a sailor with barrels of wine, it's English. And this is another one, a clock on the building that says Lavinia on it, and so on. And this can be in different languages, okay? So this is Chinese or Thai, and all those things. So just at this point, just make sure that you guys understand the basic concepts, right? So supervised learning, you learned in the 5415, imaginate given classes, in the labels, you train the model, so it's called supervised. The problem with supervised learning is that you have to have labels, use annotation. Human, if you use from web, they are noisy and they can create problem. Self-supervised learning is that you don't need labels, because you use some pre-test tasks. Zero-shot, it's not really learning, but zero-shot testing, that you don't need any labels. You train on some other model, so other data set, but apply to different data set. Few shot, where you have few examples labeled, you fine tune with those few, and then you can solve that, okay? So other is called pre-train versus fine tune. So you can use a pre-trained model, and you don't do anything to that, and that is shown with the snowflakes. Snow is frozen. And when you fine tune it, then it burns. It's a fire, flame. Okay? So then we have image encoder. Given image, we want to encode it. What's the representation? What's embedding? So we've been talking about VIT clip and so on. Then we have text encoder, T5, BERT, those kind of things. Then we have the large language model. So Vicuna, OPT, Llama, GPT, the series of large language models, lots of them. Then important thing in all these is data set. That data, is the new oil, and China is new Saudi Arabia. That was a quote from one of the famous AI researcher. So because you need a lot of people to annotate and you need to have data. So the big breakthrough has happened that when you combine text with the image, because all the history of computer vision research were looking at just image, the vision, nothing to do with text. The people you say NLP is very different from computer vision. But now with this thing, NLP is helping vision and vision is helping NLP. So image text pairs is what has made a difference. And they are available. People upload their pictures with the caption, you use it. So all these learning, when you want to learn, there has to be some objective. Learning means you want to learn the parameters of your model, right? The weights, the transformer, these weights you want to learn. When you compute, given an image, you want to compute key, value, and query. So talk about these convolution, one by one convolution, so on, in image. So we need to learn those weights. And there are lots of them. We want to learn weights for the MLP and so on. So what is the loss function, objective function, very important. So we talk about, contrastive loss in the clip. Then we talk about captioning loss. So that's easy because we have an image, we know it's captioned. So when given an image, we want to predict what it should be. So we can use that. And then other is just image text matching. So I say, well, this text matches with the image, 1, yes, doesn't match, 0. So it's similar in a way, contrastive, but it's a little different. It's easier. So task is you want to recognize objects, recognize so actions and so on, accuracy. So you give 100 tests, how many times you are correct. Or in the retrieval, given a text, you want to retrieve an image, or given an image, you want to retrieve text. It's a recall. How many of these are able to recall correctly? Precision, F1 score, and so on. VQA, visual question answering. So you have a ground truth, and you have a question. You look at the answer from the system. You compare with the answer ground truth and look at how many times it's correct. So that is called accuracy. Then the other thing, you take the match to text strings, and there are different matrix, blue and so on. So that's the other way. And the other thing you will hear, the open source models, which are available, anybody can use. And other is called the closed source, like GPT is closed source. So it works very well, but we don't know what is the data set they have used, what's the loss function, how many layers they have, and all those things. And that's the the issue, because many of the new things you do, whatever new method you develop, most of the time GPT is doing better. GPT 4.0 is doing better than any method. But still, it's a research issue that the science has to be open, right? We need to know what is being done, what are the challenges, what are the difficulties, and how we solve those. That's why still the field is going. Otherwise, GPT, OpenAI, they say they can do everything. So you can pay $20 per month and you're done, then you don't have to take these courses. So that's kind of dilemma. And many people don't understand this. So the same thing is the data set. Because data sets also, because these companies, they spend millions of dollars to collect the data set, to annotate, and they don't want to share. They're closed. But academic community, we want to make everything available, so still there's effort that you can collect data set and make it open source. Okay? And the models also, that train model, checkpoints, and all those things. The difference between open source and closed source. Okay, so we'll go back now. The next thing we are going to talk about Flamingo. And this also is from the the Google, and this is a very famous professor, most famous professor in computer vision. Andrew Zeman from Oxford professor, also DeepMind. So, so Flamingo is interesting that it has the pre-trained model. So we take the images and we have vision encoder, and then we also have the text. Suppose this is a very cute dog, and there's another sensor. This is something about a cat. And so now one thing is that text and image, there are different modalities, right? So text, we have words, and those are tokens, and the image is just pixels, numbers. So we convert page in a token, but their dimensions are different. The embedding of you talk about 16 by 16 RGB, 768 dimension feature vector. But the text normally is smaller. And also image has many, many tokens. Right? One image will have, 196 tokens or something? Lots of them. So this model perceiver will convert the number of tokens or the dimension of each token, so to align with the dimensions of the text. So now, again, they want to do this, the cross-attention, that you have this language model. There are different blocks of the language model. So each of the block, they take the text encoder and image encoder, they do this cross-attention, and this each of the layers, and at the end, they get output. So let's look at a little bit detail. So we have an image X, and we have the text Y. It's called gated X attention, cross attention. So we take input image, we make key and value, and we get the language, we make a query, and we do the cross attention. You've learned that. So then we do apply the tangent hyperbolic gating and do the skip connection, feed forward, and we do the same thing for the next layer and so on. So this is the way they are doing this. So it's a same idea of attention, that we have the take the X, make a key and value, and Q is the query is the Y. We do the attention, but then we have this additional thing, tangent hyperbolic of this thing. We add this to Y, the skip connection, and they found out that this helps make it stable, and that's it. So this layer is frozen, but then the other one is this is learned. So this is a frozen, the cross attention or X attention they're calling is learned, and that's it. So they use this 70 billion Chinchilla language model and resonate vision encoder. So here they're not using transformer, I think. Objective, again, very simple. at the end, the last function is very easy, right? So given the words which you have outputted up to L minus 1, and given the image up to L, then predict what is the probability of the word L. And that's the way they train. So they use a mixture of vision language data sets. So one is a multimodal massive web, 43 million web pages, pair of images, video, and text. And then also they are using LTIP, long text and image pairs, these many millions of image text pairs. And then also they're using video and text pairs, 27 million short videos, each is about 20-second average, and with the paired description. So they can do something like this. So you have an image, and this is Chinchilla. They are mainly found in Chile. This is Shiba. They are very popular in Japan. Then it has to predict this is what. It says Flamingo, they are found in the Caribbean and South America. So which is interesting. Yeah.
This image and text that is given before.
Yeah, this is the input. This.
It can be like a random image, or it can also be like animal here, or it can be.
Yeah. So you have to have the image and corresponding text for that, describing another image, corresponding. Then you image and you ask to fill in the blank.
No, I'm asking whether that previous image and the text has to be like relevant to the final image for which we want the answer, or it can be anything.
No, it is, doesn't have to be. I will show some more examples. Maybe I'll come back to that. Okay, so in a way you can say, yeah, maybe it's in context learning. So because these are the paintings, and there's another painting, and it's asking you. So what is the title of this painting, and what's the title of this painting, and what should be that? Yes, kind of in context learning. Same thing here, and so on. So it's pretty interesting, right? So, 10 years ago, we never thought we can do it. Computers can do that, which is really good. So then you can do the conversation. This is a picture of two teddy bears on the moon. What are they doing? They are having a conversation. What objects are they using? It looks like computer and all this thing. Then what is the common thing about these three images? And so you can put any number of images. And that's why they are able to put the video. So video is a series of images you can put in those. And what's the difference between these three images? And you can answer this also. And things like that. Okay? So they show the results. Again, at the end, you have to show this works. And you have to show with all these data sets, right? So what they are doing now, that once you train this, then they can do all these tasks in few shots. For these data set, for these tasks, they were not used. The trained model did not use this data set. But now they want to use only 32 shots to solve these problems. And they are comparing with the state-of-art methods, which are fine-tuned on these data sets. Okay? So you could choose this method, actually use that data set, and this one, MSRVTT question answer was trained on this data set, performance of 41, but here they use only 32 shots, their performance 66. So they are doing better than fine-tuned model, right? So all these. In these problem, there's no method which does that, so this is their 62 in all this thing. And for these problems, they are actually going beyond So 100% is the maximum, but they are actually doing better than the models which are fine-tuned on this data set, like Flickr and IVQ and XQA. So which is very impressive, right? So you can take a model which uses this as an XQA, and but this model which uses only 32 shots, it can do 33% better than that model. So which is good. Okay, so there's another model called FLAVA, Functional Language and Vision Alignment Model. So here we have the multimodal, unimodal training data set, image and text pairs, unpaired images, unpaired text, and this is the model. And you can, once it's trained, we can do visual recognition, like you can do ImageNet classification, you can do language understanding, you can do multimodal reasoning, VQA, and so on, just one model. And the good thing about them is that they use all the openly available data set. As I said, some of these data sets are not available, so you cannot use, they don't release. But these are data sets available, so they use about 770 million image pairs, and this is average length text. And so this model is interesting, so you want to listen very carefully. So you have an image, and you have image encoder. So you have these tokens, CLS token, the beginning of the image, page 1, page 2, and all this thing. And it goes to image encoder. Then you can, once it's done, you can do ImageNet classification. So they have this vision task head. Similarly, they have the text. Again, you encode the text. You have the different encoding and text encoder, and you can do the NLP, natural language task. So it's in a way, image and text. Then they will combine this, that you can do now multimodal. Multimodal means we have two modalities, text and image. And this is the multimodal encoder. So in order to train this, you need to have all those losses. So for this one, they use mask image modeling. Remember we talked about mask autoencoder. So you take an image, you take some pages, you mask them, and you predict the mask tokens, and you learn that way. So that is the what they are doing here. And here also you can do the same thing. See? So the conceptually learning can be applied different modalities, same idea. Here you're masking the tokens or pages and predict those mask tokens. And here you can mask the words. Words is a token, image page is a token, and you can do the same thing. And the reason you can do it because you know that you have masked it. You know the ground truth. You can compare with that. So that's that. Then in this one, they are using image text matching. So you have an image and a text, the correct, say 1, if it's incorrect, 0. And then they have multimodal modeling, mask multimodal modeling, where you will mask the token image, you can mask the text, and you can predict the both. And then you can do the global contrastive loss also. So that's it. So now if you compare this with CLIP, so CLIP in a way was very simple. That's the beginning of the visual language models, right? Very simple image encoder, text encoder, contrastive loss. But here they are doing different things. As you see, this model is much more sophisticated as compared to the CLIP model. So that's why they are doing better than CLIP in many of these tasks, right? That's what they compare. But of course, some of these, they are not doing that well. Here again, you can see UCF 101. Okay, the next one is called Painter. And this is also very interesting, and this actually uses the in-context learning. And so Panther. So it rapidly adopts various tasks, and it basically painting. The Panther is model which is image-centric solution, and given an input image, inpaint the desired but missing output image. Okay, so they use VIT large, and then loss a very simple L1 loss. Okay, and so here is what they are doing. So you have these two images. This is the image and like a segmentation. Then, so which you are giving as a ground truth. Well, for this one, this should be the output. And then you give a new image and you want to ask output this image, and this is the output. Similarly, for this one, you tell it that if you give this, this should be output. Now you are asking, give this one and tell us this. So it can do these different tasks, which is very interesting. So it can do semantic segmentation. You want to label each pixel with different labels. Okay, this one is instant segmentation. So even though there are two people, so we segment them, but we have different colors. Person 1, person 2. Here you want to estimate depth. You want to say each pixel how far it is. And here you want to detect the joint key points. And here you just take a noisy image and you want denoise. And here you want to remove the rain, deraining. Here you want to enhance the image, the text image. And now these, they had examples they trained, but given this trained model, they can actually solve new problems, which is they can do object segmentation, key point detection, instant segmentation on completely different cases. So the model works very intuitive. So you have the image pairs. So this is input, this is image, this is output. This will be semantic segmentation and so on, as I told you. So you put these image pairs. So from this, you take two pairs, say this and this, and put them one image. And then do masking. So some randomly, you mask those pages. So like this way, the mask image autoencoder works, right? So then you try to learn those using a vision transformer. So these are the missing pages, and these are the ground truth, and these it has to predict. So basically you learn the vision, and that's it. So once you can do that, you can do all these things. So of course you have to give examples. So this image should be this output, and this is a ground truth that can do it. This image, this is their prediction, this is ground truth. So it's pretty convincing, pretty good. So now we'll talk about the last model, which is the BLIP2. And this will be your assignment, so you want to listen carefully. Again, you can see all these are very similar things. That's why they are kind of linked together. So you have to keep building, adding knowledge to what you are learning. This is pretty influential paper from Salesforce, BLIP2, and it's kind of derived from CLIP, right? So you're saying bootstrapping language image pre-training with frozen image encoder and large language model. So CLIP did not use large language model, just some simple image, text encoder. Okay, so the idea here is that you use image encoder like a CLIP, but you do additional thing that you want to extract the relevant information from an image based on the text. So these are the queries. So you want to, the queries will be learned, and these queries in a way is extracting the useful information image based on what you are asking, what your text. Okay, so it's a very interesting idea. And they call this Q transformer. And once this information is extracted, then goes a large language model. It's frozen, and you can do lots of things. So that's the main contribution, that typically you will just take an input image, get a clip, and just go here. But here, this Q format, their contribution. Okay? So how it works. So you take an input image, make the tokens, and then this is the Q format. And so queries are, again, like a tokens. So here we are showing the several tokens, and they are randomly initialized, and we will learn those. Like we learn the weights of the CNN or transformer, we learn these weights also. Okay? So that's the idea. And we learn so after learn, they will extract the correct information from any unknown image, which is very nice. So since it's a transformer, so we'll do self-attention, then cross-attention. Now self-attention of these queries, and then cross-attention with the image tokens, and then feed forward. So this is for the image, and here's a text. So self-attention, then feed forward. So now if you fill in the blanks, so first will be image to text matching. So you have an image, and with corresponding text, we say 1, if it is not 0, simple. Then this is the image text contrastive learning, the clip loss. Okay? And this one is the image ground text generation. Based on that, we generate text with like captions. So these are the 3 losses they are using. So now, important concept here is how they are using this attention. Okay? So as I told you, that there are these query tokens and there are text tokens. Okay? So we will represent the tokens with a mask with the filled in square and unmasked like this. So let's assume we have 2 query tokens and Q text tokens. When we are doing the cross attention, now we have 4 tokens, 2 query, 2 text. So standard self attention will do, each token will pay attention to all other tokens, right? So now, but here since there are 3 different losses, so they have different ways to do it. So here, image text matching, we will, each of the query token will be used in this query tokens and also text tokens. So these all are unmasked. It's a standard self-attention kind of thing. Here, when we use image ground text generation, because we are given an image and we want to generate text, so this is the predict the next token. So therefore, it has to be causal. So here, the when we have these 2 query tokens will pay attention to self, but the query token will not pay attention to text tokens here. So also text tokens, these are the they will pay attention to these will pay attention to itself, but then when you look at these text tokens will pay attention to query tokens because that's fine, because these are learned. But when they go to text one, so the first token will pay attention to the first one because we know, but we don't know the second token yet. So it will be masked. Okay? The second token will pay attention to first one and second one. So that's causal because we haven't seen the second token yet. So therefore we'll mask it. So that's an important concept here. And then image to text contrastive learning, which is the same thing, that query tokens will pay attention to query itself, and the text will pay attention to itself, and these other will be masked. So it's like what we were doing there, in the clip. So That's it. So this is called in a way stage 1. So here we are learning the Q former with the 3 losses. To basically we are learning what information we want to extract from the image based on the text, and cross attention using the text and image in the causal way, and 3 losses. So the next stage is that now we take the image, get the query tokens out. This is the relevant information in the image. We extract it. Then we put that to the LLM, and then LLM is frozen, large language model, and we get the get the output. So that is one way that we have decoder, but we can do also encoder and decoder. So the difference in the when we're using the encoder and decoder, that we can do the autoregressive fashion, that we can take what its output. Here is outputting a cat wearing a sunglasses. So when we are, predicting the wearing, we can feedback a cat, the second word, and when predict the wearing, then we can feedback the wearing to predict the sunglasses. It's called autoregressive. It's coming back, right? So we are using that information. So they use the VIT L14 from Clip as a frozen model, and they use the EVA Clip also. In LLM, they use OPT and T5, and data set with 129 images in total, and that CoCa, visual genome, and all those things, C3M, and lots of them. Okay, so these are the kind of images you can get output. Explain the advantage of this product, and you go through this thing. Tell me something about this history of this place. You can do conversations, blip too. Okay, and they show that they can do better than like Flamingo we talk about, right? So this is 56%, 65 VQA, and similarly here's 97, 89, and so on. Now, so your GTA, so Savita is not here. She had a paper last year in ECCV, which builds upon blip2. It's called XFarmer. And the idea is, as we just discussed, that it is the main thing here is the XFarmer, and which is extracting the information from an image in terms of queries, and it's using the image encoder, which is from Clip, which is frozen. Okay, so and it's using contrastive learning for the contrastive learning was used for Clip encoder. Remember I talked about earlier, another way to learn in self-evident manner is called MAE, mask autoencoder. So you mask these tokens, put encoder, and you predict those mask tokens, and that's the way you learn. And this representation can be used for the image representation. So what Savita did is introduce this XFarmer. So essentially introduce this MAE encoder, another way to encode an image in addition to Clip, and that made a difference. So, this is the MAE, and then you do the MAE, you take the image, you master tokens, you predict this one, and that's a standard thing, mask autoencoder. But the difference was that you take also the image from the QFarmer, get the queries, and do the cross attention between this MAE encoder and also the Clip encoder. So you're using both information. Clip is contrastive, MAE is the mask autoencoder, and you combine those. And then again uses same losses, image to text, contrastive learning, image text matching, and image text generation. And at the end, the second stage, as we say, will be given an image, you apply these two, and you go to the XFarmer, you get this representation fully connected, go to LLM decoder, and you get this. So, and that works better for these kind of problems. So say how many donuts are in this image. The blip will say 4, but actually 6. How many airplanes are there and how many? So it works better in counting because capturing the fine-grained information, because the autoencoder, mask autoencoder, you're masking these things. The contrastive clip is global. You look at the CLS token, you do this. So like this, you can talk about this. And then it made a difference in this data set 25, 39, 21, 27, and so on. And also, you can compare with the GQA, GQA, and this data set also made a difference. So